All right, folks, let's get started on looking at 1.4. I'm going to try and keep this as short and sweet as possible. So pull out your hard copy that I provided on Friday so that you can take notes alongside with me. We are looking at this box that says polynomial functions and has this big, long expression in it. P of x is frequently used to refer to a polynomial function in terms of the variable x. Now there's a whole lot more here than just x's, but let's break it down just a little bit. We have coefficients, a sub n minus 1, a sub n minus 2, a dot to symbolize we keep following the pattern previously established until we get down to the point where we have a sub 2, a sub 1, a sub 0, and you hear me saying a sub 1, that is a subscript the unit 1. So we have, this is what we call sequence notation. So these are a sequence of real numbers, a sub I for any indice, 1 through n, 1 to n being the largest indice, where a sub n is non-zero, because if this first coefficient was 0, then we'd multiply x to the nth power by 0, and this term would just be 0, meaning it wouldn't be an nth degree polynomial, it would be an n minus 1th degree polynomial. So this coefficient, it's really important that it does exist as something other than 0. The leading term, you know this term, this is going to be the coefficient and the variable to that highest power. So notice how the powers are counting down n minus 1, n minus 2, and follow the pattern until we get down to 2, an implied 1, and an implied 0, right? X to the 0 power is 1, so there's no x in that last term. This is the same pattern you used to seeing with maybe quadratics, ax squared plus bx plus c, or cubics, ax cubed plus bx squared plus cx plus d, right? Our a, b, c, and d, or a, b, c, is following that pattern of coefficients. And then we see the variable of interest, the input variable, being raised to the highest power, then the lowest, then lower, one lower, and decrement all the way down until we don't see an x anymore, the 0th power. These are the building blocks of our polynomials. We may be pretty familiar with quadratics from Math 2 and cubics more from Math 3, and even higher degree polynomials, but they can go as high as we want to. So this is what we call a general form of a polynomial, and I'll actually leave that there. A general form, so that we can build that pattern with symbols rather than necessarily building out all the lists, right? If we were listing out all the different versions, that would be an infinite list. Here we can represent all of the infinite different versions up to degree n with one expression. So that highest power appearing in the leading term, where the term is the whole piece, the degree is that power, that highest power. For a cubic, the degree is 3. For a quadratic, the degree is 2. The leading coefficient is just that number being multiplied by your x. So leaving out the x, the leading coefficient is just that piece being multiplied. It is a real number. It may be rational or irrational. And our degree we see in that highest power. All right, so let's look at a couple examples. The leading coefficient and degree of the polynomial function are both going to come from the leading term. Now, sometimes if a function is in standard form, that term is in the front, but sometimes we're not so kind. The first example, A, with f of x, our leading term is 3x to the 4th, so our leading coefficient is 3 and our degree is 4. But our second example is not so kind, because 12x is up front, but our highest power can be found in that second term, negative 7x cubed. So the leading coefficient is negative 7x, or sorry, negative 7, I misspoke. And the degree is 3. So it comes from that leading term. It's called a leading term because in standard form it should lead, but something's not always presented to you in standard form. Now, this whole term, 4 by itself, is the leading term. This is a constant function, and technically it does meet the definition of a polynomial. That is where n is 0. And actually maybe it doesn't, because our definition says where n is a positive integer, and a sub 1, yep, where n is a positive integer, n is the degree, and degree 0 polynomials, 0 is not positive. It is an integer, but it's not positive. So technically this is a degree 0 quote-unquote polynomial, but based on this definition, it doesn't technically meet the definition of polynomial, but it follows generally the same rules, just very simple. When we see a constant function or even a linear function, degree 1 polynomials, we're generally going to refer to them with their more specific name as constant or linear, not necessarily polynomial, because they are that specific type of function. So our leading coefficient is 4, the degree is 0. This is y equals 4, a horizontal line. Now the big topic for this section is extrema, meaning extreme values, the highs and the lows. There are two types of extrema. We have relative extrema or local extrema. Those terms are used interchangeably. Relative, meaning relative to the points around that place. So just within a locale, just within one space. Versus absolute refers to the entire function overall, global. The entire function's domain. So a polynomial has a relative minimum or a relative maximum always when the function switches between decreasing and increasing, or vice versa, or at an endpoint if we have a restricted domain and that point is relatively lower or higher than the points around it. For example, this first endpoint is a relative or a local minimum because it appears lower than the points around it. Even though there are only points on one side, it is a low point on this graph. So that is a local minimum, and it'll go in our list at x equals -4. Even though the value is -3, that would be the minimum, the local minimum value. But if we list local minimums, generally we just want to list their locations. We don't care how high or how low they are as often, just their location, x values. So we have another local minimum when the function switches from decreasing to increasing, and that is at x equals 0. And there are no more local minimums. Now you may be looking at the right side, but since this function has an arrow, it's going to continue on down forever and stay decreasing and never have an endpoint. So that means there can't be any more relative extremas down there. So if we focus on maximums then, our maximums are where the function switches from increasing to decreasing. So from low to high, high to low, a high point, if you will. We have 2 of these, and they appear at -2 and at +3. Remember, we're listing x values, x equals. All right, absolute extremas have to do with the entire function. So an absolute extrema is always the very edge of the range. End of the range. You may think of end behavior of the function as what happens to the y when we look at the ends of the domain. Well, absolute extrema looks at the values of the function at the very ends of the range, so focusing just on the y spaces. We do care about their location, their x value, but in this case we're also going to care about the y value a little bit more, because we can see that this function has an endpoint on one side and decreases without bound on the right side. So anything that we see in this picture is the highest values we're going to get. And the absolute highest value we see, the absolute highest, is at x equals 3. That is an absolute maximum, the value of which is 2, and the location is at x equals 3. That is an absolute maximum. Now, if the right side were not an arrow and it were an endpoint, we might also have an absolute minimum. But because this function keeps going down forever, when a function decreases without bound, then it can never ever have a relative minimum, because it will always be able to find a lower piece. So there are no absolute minimums, and I'm going to write NA in these blanks. There is an absolute maximum, there is an absolute highest point. The range of this function is from negative infinity up to y equals 2, but it does not, because the range goes all the way down to negative infinity, it cannot have an absolute minimum. We can always find a lower value. So that covers our 2 types of extrema, and that's what goes in the blank up there. I'll leave practicing a sketch to you, and if you'd like to check it with me at office hours, you're welcome to do so from 1 to 2 p.m. All right, example 2, find and classify. Maybe pause the video here, check your understanding, and then come back and see if you get those answers right. All right, so let's look at these answers together. You've had a moment to pause. A relative minimum on this graph, well, a relative minimum is either an endpoint, and there's no endpoints, or a place where the function switches from decreasing to increasing. And remember, we're always reading left to right for those. Now, reading left to right, I see increasing behavior and then decreasing behavior. So that spells out a relative maximum at x equals 1. There are no relative minimums on this function. There is one absolute maximum, and it is also a relative minimum. Relative maximum. All relative maximums are candidates for absolute maximums. Except, that would not be an exception. All relative maximums are candidates for absolute maximums. If it's an absolute maximum, of course it probably meets the criteria to be a relative maximum as well, but we use that more specific name rather than calling it relative and absolute. We just say it's absolute, and it implies it's probably also relative. So our absolute maximum value is 3, and it occurs at x equals 1. There is no relative or absolute minimum. All right, you've had some time to practice B and C, but if you didn't already pause it to do these, pause, and let's check. Relative minimums occur at x equals -2, and that should be it, no commas. There is a relative maximum at an endpoint and where the function switches from increasing to decreasing. I'm putting that at about x equals 3, so we have 2 options, -4 and 3. Notice I'm just listing the x values for relative minimums and maximums. Absolute maximums, the absolute minimum, there will be none, because notice this arrow goes down. The range is going to be from negative infinity up to a finite value. So on that infinite side of the range, there is no absolute minimum. But there will be an absolute maximum at that highest of the relative maximums. The value of the absolute maximum is 2, and it occurs at x equals 3. Notice how that is a relative maximum as well, but its most specific name is absolute. Last but not least, we have a relative minimum at x equals -3 and x equals +3. I would call these endpoints relative maximums because the points near them are below the function, or below that high point, and as well as a relative maximum where we switch from increasing to decreasing. So the relative minimums occur where the function switches from decreasing to increasing, negative rate of change to positive rate of change, and that list includes -3 and +3, and our relative maximums are at -4, 0, and +5. Now our absolute minimums, there's only one for each. This function has endpoints, so it is possible to have both an absolute and a maximum. Polynomials can only have either one, because they'll always have, at least as long as we don't restrict their domains, because they'll always have an infinite side of the range. If both sides of the range are infinite, then there can be neither. And if one side of the range is infinite, then there can't be a max or min in that direction, right? So if the top side of the range is infinite, then there can be no absolute maximum. And if the bottom side of that range, like negative infinity, is infinite, then there can be no relative or absolute minimum. So in this case, we do have both because our range has been restricted, and our domain has been restricted on both sides. So our absolute minimum function, minimum value, is -3, and it occurs at x equals -3, and our absolute maximum value is an endpoint in this case. The value is 4, and it occurs at x equals 5. So some fun facts about polynomials. When you consider the entire domain between two real zeros of a polynomial, there must be at least one relative, and let me spell relative like relative correct, relative minimum or relative maximum. There must be an extreme value between x-intercepts. And we can use the graph above, the several graphs above, to kind of demonstrate this. If I look at these two x-intercepts in green, these two x-intercepts, if I touch the x-axis twice, between that, I leave the x-axis, I must come back to the x-axis. That behavior of increasing to decreasing causes that change from positive rate of change to negative rate of change, and we must see a relative maximum above the x-axis with that in that case. Or on the graph to the left, if we consider these two x-intercepts, we cross below the x-axis, negative rate of change for a decreasing function, positive rate of change for an increasing function. Between that change, we have to have a relative minimum. So anytime we touch the x-axis twice between those two consecutive x-intercepts, we must have an extreme value. Now, polynomials of even degree must have either an absolute minimum or an absolute maximum. And remember, global means the same thing, global minimum or global maximum. Because polynomials of even degree, think about quadratics, even degree, 2, 4, 6, 8. So quadratics and quartics we're pretty familiar with. Quadratics look like this, right? They're symmetric. They might be reflected, but our positive x squared, our negative x squared can both represent how this can be true. Even degrees will be symmetric. They will, or not always symmetric if you start seeing above quadratics, but quadratics are always symmetric, so they kind of demonstrate this. But our end behavior will always match on either side. The end behavior will be symmetric, I should say. So that means that if only one side will be of the range will be infinite, and there will always be a lowest point or a highest point. But as soon as you see odd polynomials of odd degree, like cubics, you'll start to see that both sides of the range have to be infinite, and there can't be any absolute max or min. So the degree of the polynomial and its end behavior can influence that. I'll leave this practice question for you, and I'll have at least one example in the key for you to check and compare your answers with, but there are multiple answers to that one. All right. Let's see how many more pages we got. One more section, and then you're on your own to practice. So our points of inflection, we've mentioned this before, but a point of inflection is a place where our function changes from concave up to concave down, or vice versa. So our rate of change will switch from increasing to decreasing or decreasing to increasing. Remember that the rate of change can be increasing even when the function is decreasing. Those are different things. So we want to associate rate of change increasing and decreasing with concave up or concave down. So let's look at our graph example here and try to find our points of inflection. Now, we're not necessarily going to be able to calculate exactly where they are. We're going to kind of ballpark it in pre-calculus, but we do have a way to know a space where they must be guaranteed, because around a relative minimum, the function must be concave up, right? We know that at a relative minimum, we draw that tangent line below the function. So we know the function is concave up, both on the left side and on the right side of that relative minimum. So our function decreases at an increasing rate and then increases at an increasing rate. However, at the relative maximum right here, if I were to draw my tangent line, this has to be concave down, and it must be concave down on the left side and on the right side. So from our concave up section to our concave down section, somewhere in between these extremas, there must exist some change in concavity, and that is a point of inflection. So we can guarantee that between two relative extremas, there must exist at least one point of inflection. So I'm going to say that we're ballparking this, but it is a pretty good guess. X equals -1 is a location. I see another relative minimum at x equals 2, so I know our concavity needs to change again, and a pretty good guess there would be x equals +1, as I can see that change in shape occurring there. So +1 is also on the list. Now there are no more relative extremas on this graph, so that behavior of concave up will continue towards infinity on either side, right? The function is concave up at the beginning of its domain and at the end of its domain, and so that pattern will continue on into that infinite end behavior we can't necessarily see, but we assume it keeps following that pattern. And I must have accidentally erased this. So -1 and 1 are points of inflection. So it says, for each of the following intervals, determine if the rate of change is increasing or decreasing. If we ask about the rate of change increasing or decreasing, we're asking about the function being concave up or concave down. So from 3 to 4, we're asking, is the function concave up or concave down on this interval? Notice we just left a relative minimum, and we're always concave up around a relative minimum, and we are not approaching another relative extrema, so it is going to keep the same behavior and stay concave up. So since the function, we're going to explain our reasoning, since the function is concave up on the interval 3 to 4, the rate of change is increasing on this interval. All right, from -4 to -3, we have kind of the same situation as before. We see this function behavior happens just before a relative minimum, and it's coming from that end behavior. So we're going to see concave up behavior around the relative minimum and all the way to the end of the domain. There's no other relative extremas telling me to change. So the same reasoning applies, just for a new interval. And it's always good to mention your interval. And I'm going to duplicate this and just change my interval. You don't have the same magic buttons, but it's good for you to practice writing it down. So let's change our interval from 3 to 4 to be -4 to -3. Same reasoning though. The function is concave up, so the rate of change must be increasing. You pause, try -1 to 1 and 1 to 2, and then come back and see if you got it right. All right, from -1 to 1, I see that's in the section I highlighted red. Around my relative maximum, this function is concave down. So I would say on the interval on -1 to 1, the function is concave down, and therefore the rate of change, which is what we asked about, the rate of change is decreasing. All right, last but not least, we have 1 to 2. From x equals 1 to x equals 2, this is my section I highlighted in green. It's after that point of inflection we named at x equals 1 and approaching a relative minimum. So this is a concave up section. So on the interval from 1 to 2, and it would be even better if I wrote the words the interval, but I'm getting just a little bit shorthanded. On the interval 1 to 2, the function, notice how I do not use the word it. I say the function is concave up, and therefore the conclusion I can draw is that the rate of change is increasing. All right, so there you go. You've got some notes to use to reference. If you will, please attempt the practice in the rest of this packet and then upload your work and check it with the key to make sure you understand. I will be holding office hours from 1 to 2 p.m. If you have any questions, please log on and ask them there or shoot me an email. I look forward to seeing you back at school as soon as we can get there. Have a great day.